Welcome to the video on linear regression. So what is linear regression? It is a linear relationship between a dependent variable and independent variables. So as we have already discussed in the previous videos on machine learning and stuff, that basically the purpose of model building is to be able to predict a dependent variable. So there are independent variables and dependent variable. Dependent variable is also known as response variable, and independent variables are also known as predictors, or there are different names such as explanatory variables. So just remember this, that independent variable is known as explanatory variable or predictor, dependent variable is dependent variable basically, or response variable. So this is the purpose of linear regression, where basically dependent variable is a numerical variable, and depending and it and we look at the linear relationship between dependent variable and independent variables. We'll see with examples how it works. So using a mathematical equation, we find the value of a scalar response. That's what it means, that dependent variable is a numerical variable, and depending on this, we write down a mathematical equation which uses dependent variable as well as independent variables. And basically the purpose is to be able to find out the value of dependent variable based on independent variable or explanatory variables. So only one predictor in a linear regression, you can only have one predictor. No, sorry. What I mean is you can have one response and multiple predictors. So what it means is that a linear equation or linear regression can be based on one response variable. Response variable is always one, but there could be multiple independent variables or predictors. But when there is only one independent variable or one predictor, that is, then this linear regression is called simple linear regression. So if there are more than one predictor and a response variable, then it is called multivariate linear regression. Multivariate itself means multiple variables. So let's look at how it works. So here is y is equal to theta 0 plus theta 1 x1. This is the example of simple linear regression. This is the mathematical equation. So this x1 is independent variable and y is dependent variable or response variable, and this is also called predictor or explanatory variable. If you have more than one independent variable, which is the example of multivariate linear regression. So here is the mathematical equation of multivariate linear regression. So you have this response variable theta 0 plus theta 1 x1, x1, x2 to xn, they are all independent variables, and this is the linear equation. Now what is theta 0 here? Theta 0 is basically known as bias term. So all these thetas in machine learning or statistics or data science, they are called coefficients. So this is basically also coefficient, but it is called biased term because even without independent variables, this is the value of predicted value of y. So if you are building a baseline model, which we'll come to know later, then without any independent variable, then you just get this value for all the value for all the values of y for all the records. The only value that this model will predict is this theta 0, which is basically a mean, you can say. Sometimes it's mean. So wherever it intercepts the y section, that is what it is. We'll go into details later as we build the models. So for example, if you want to predict the sale and your independent variable is price, then this could be the equation theta 0 plus theta 1 into price. Now for multivariate linear regression, you can add one or multiple variables. So this equation is the same, plus we have added one more independent variable, which is number of customers. So this becomes multivariate. So what is the idea in linear regression? So we'll look at one example and try to understand what it means. So I've just created one dummy variable called sale, and this is going to be our response variable or dependent variable, and this is a predictor or independent variable. So just two examples I've just randomly created here, and then let's plot this example on a graph. So this is a scatter plot. For now, just ignore this line. Focus on these dots. So these are the dots. These are the points, actually data points. And in data science, these points are also called records or examples. So this is one example. This is another example. This is third example. So each row is considered as one example or one record. So just remember that. So the scatter plot only includes these dot points where this y-axis is sale and x-axis is price. And so this is what we have plotted, and then let's see. So lm is the function used in R. I've just jumped to the function, not to explain the function itself right now, but to show you how this linear regression works. So don't worry about this function right now. Just focus on the idea here. So I've just given a name to this model. So LM, if you use LM and inside the bracket the left side of the tilde, this is tilde, left side of the tilde is your response variable and the right side of the tilde is your independent variable. If you have multiple independent variables, then you just use plus sign and keep adding those independent variables. So it will create that model for you. This is very simple in R. So then using this model, I have created this line. So there is a function called lines in R. So to plot a line, you can use this function. So you need to provide x and y coordinates and color and other parameters. So basically price is what I have taken as independent variable here, but instead of sale, that is y-axis, I'm using the value predicted by this model. So there is a function called predict, and inside the bracket you mention the model itself, which your LM function has built. And what it will do is it will automatically pick up the x values. You know, this predict function will automatically take these value, because we are not separately providing another value. If you want to predict a different value using this model, then inside this bracket there is a another argument for new data, and you can provide that new x values, and it will predict the y value for those x values. Or x, when I say x value, I mean independent variable. So if you provide the new data or values of new data of independent variables, so this predict function will predict the uh, unknown values of sale, or the dependent variable. So this is what this function does. If you don't provide any new data, new independent variable values, then it will pick up the one which was supplied in the function lm itself. So what it is doing right now is it predicting these values, but uh, based on these value, it's predicting the new values for the sale. So we'll see what is the result here. So if you want to see what L is doing, uh, basically it create it uses the function lm, and it comes up with the values of coefficients as we discussed, right? So what is sale here? Sale, the formula would be sale is equal to theta naught plus theta 1 into price. That's what we saw in the previous slide, right? So what we are trying to calculate or estimate is the values of theta 0 and theta 1, the coefficient. That's what we are trying to basically come up with, in a model building. That is the main essence. So this model has calculated this value for theta 0 and this value for theta 1, and that's how it has built the model based on historical data. So, and when you plot this line, this is what you get. So what you see here, this line is your model basically. This line is the model. So you see it's a straight line. Of course, uh, uh, this is based on the very limited data that we have here. I have given very small data, and yet this function has done a good job here by predicting this model. So you see these are the predicted values here. See, for price 3, the actual value is 10, but our model has predicted 8. For price 35, the sale value is 12, the original value is 12, but our model has predicted 14, right? So then likewise, if you see the third value 16, which here it is 15, then 18, you see, and here also it is 18, so it's quite accurate here. 20, 19, 21, 20, 22, 21, 23, 21.9, almost 22. So you see, our model has actually done pretty well. Uh, so, and those values are falling on this line, right? So for 8, it is somewhere here down. It will be down somewhere here. For second value, which is 35, the actual value is 12. So it is 12 here actual value, but our model is predicting somewhere here. So you see, this is what this model is doing. This line is the model, and these are the points. So basically, our job is to build a model which is something like it, like this, with minimum error. We'll see later what happens. So if you want to know the more details or the more information of this model L, you can use a function called summary, and this will and inside the summary you mention the name of the model, and it will give you all the details. So see the formula, then the coefficient that it has calculated for intercept, and then the price. For time being, just remember one thing, this is p-value. We will discuss p-value and other statistical measures later, but in this video, just for the sake of it, just remember the p-value for each coefficient should be less than 0.05. Just remember this. It's based on hypothetical tests and all that. We will do later. We'll do a video on all those statistical values and stuff. But for timing, just remember the p. This gives the p value. So if the coefficient, if the variable is valid in the model, then the p value here should be less than 0.05. So anything less than 0.05 is acceptable. So this model performs well because for the intercept it is less than 0.05. For price also it is less than 0.05. So it is good. And also remember, R square and R adjusted we are going to discuss in the same video later. So basically, if it is the higher, it varies between 0 and 1. So closer to 1, then that means the model is performing well. If it is less than is closer to 0, that means model is not performing well. Same goes with F statistics. We will discuss all these later. Overall p-value of the model is again 0.00029. So that means it's better. It should, p-value should always be less than 0.05. Just remember that for time being. We will discuss what p-value is, what R and R just did, and everything else later. So what are the benefits of using linear regression models? So now we look at some of the cases here. So if LRM, I've just used the short form of linear regression models. So LRM can help businesses make estimates or forecast of sale in coming months based on past trends. So as you know that these predictive models are built on historical data. So our linear regression model can help businesses understand based on the past trends. It can help businesses understand how the business is going to perform in the future. So they can use the new values of X or independent variables and predict the future. So they can know what is going to be the future trend. So again, it can show whether it is going to be upward trend or downward trends in the future. And based on that, companies can always take action. So they can predict, LRM can make predictions for the companies about their business, and companies can plan their future actions in order to increase the profitability. So that's where it plays a very important role in businesses. So LRM can also predict what would be the impact on the business if company makes certain changes, like in terms of increasing or decreasing the prices of the products or changing the value. So there also this linear model can help them, or any predictive model for that matter. So we are going to see some examples here. So we can predict the pricing of, let's say we are in the sale of old vehicles. So if the vehicle comes to us we can looking at the different parameters such as the brand, model, age, mileage, travel history, insurance data and stuff. Suppose we've already built a model based on our historical data. If we put in all these details in the model, our LRM linear regression model can predict what should be the actual pricing of this old vehicle. So this is one simple example. of what linear regression can do. Now let's say we are into charitable business. So based on, like, again, if we have a model based on historical data, so looking at demographic data, age, gender, income, education, etc., we can predict how much donation we can expect from a person or from the group and all that. Then life of a machine. Let's say we have a machine and then we build a model, predictive model, linear regression model based on historical data. So we can put in these independent variable data like vibration, sound, fuel consumption, heating of this particular machine, and this model can predict what is the life of this machine, how long it's going to survive, all those things. Also delays in the flights. Let's say based on data like, distance is going to travel, the airport, the climate condition, airline, the company, departure time. Based on all these data, our predictive model can predict that if the flight is going to be delayed for how long. This is, since linear regression, we can also, in classification model, we can build whether it is going to be delayed or not. But here, since it's a linear regression model, it can also predict the exact delay, the amount of delay. So let's see how do we basically, how does this linear regression work? What are the mathematics behind it and all that? So we've just described the equation, but how to arrive at the values of those coefficients? So what all happens, behind in the machine learning, or what are the mathematical formulae and equations and assumptions we use? We are going to see that now. So again, I've taken the same example from the previous example just to explain. And as we saw, these are the predicted values, right? So this is the plot, the same plot that we saw in the previous one. This is the model we have built, and these are the actual values. So what is least squares error? We are going to see it's an important aspect of linear regression, because this is what we use as a cost function, and we'll see all the details. So what we do is we calculate the error. So this is the actual value, and this is the predicted value, right? So the gap will be the error, right? So we are symbolizing this E2 cap. This is your error 1. This should be error 1. So this is error 2, because there is no space here. So I have left out those points only wherever I could draw the lines. I have taken only those points here. So E1 will be here, E2, E3, E4, and likewise E8. So these are the basically all these, the difference between the original value and the predicted value, that is the error, right? So we minimize this error basically. That makes logical sense, right? We want to minimize these errors so that our predictive models is highly accurate when it comes to predicting the values, right? So if we minimize the error, we get the higher prediction and better results, right? So that's the whole idea. So what we do is, instead of minimizing the absolute value, we take the square of each error, sum them up, and then we try to minimize that. That is the whole idea. That's why it's called least squares error. So we are squaring the error and then minimizing it. So least means we are minimizing that error basically. That's the whole idea actually, to get the best result. So it's the short form is sum of square error. So this is sum of square error, right? For each example, we are calculating the error, squaring and summing them up. From 1 to m. M is basically your value, the number of examples in the data. So least squares is the cost function basically. It is known as a cost function in data science term or machine learning term. And basically this cost function, we solve this cost function to come up with this linear regression equation. So let's understand what is cost function. Okay, so least square is a reasonable choice of cost function as it is based on probabilistic assumption. So basically what is the idea is that error in whenever we are building a linear regression model, or this is an assumption, and this is where also a rule that needs to be followed when we are building a linear regression. Otherwise the linear regression model will not work. So one assumption, which is one of the most important assumptions in linear regression, is all the errors must follow normal distribution. That is Gaussian bell curve that we saw in the previous video, right? In case you have not checked that video, please go and check that, go through that video to understand what is normal distribution. But I'll give you a brief. So normal distribution looks like this. Okay, the bell curve, Gaussian. this is the mean. So this normal distribution is controlled by two parameters, mean and standard deviation. So all this you see, this is one standard deviation, this is 2, 3. Here again on the left side is negative. So all the values, whatever the area we cover inside this, that area is the probability of finding those values within this range. So the rule is like from within minus 3 standard deviation to plus 3 standard deviation from mean, 99.7% of the value should fall within this. So the idea is we want to calculate the exact bell curve for our error. That is the whole idea. Now, when we want to do that, we want to make sure we know the height, right? We know the shape of the curve, that it follows the bell curve, but we don't know the height and width. So one example is this of bell curve. Another example of the bell curve could be like this. So this is what we are trying to find out here, the maximum likelihood. What it means is we want to draw a curve which gives us the maximum probability of finding all the errors within this range. That is the whole idea. So we want to find out whether the bell curve should be like this, or it should be like this, or it should be even more flattened. We don't know. That is what we are trying to. That's what likelihood means. Now, as we have seen in the previous video, that the equation of this normal curve is this. So 1 by sigma is your standard deviation, square root of 2 pi, exponential of minus in the bracket. In there what we had seen was xi minus x bar whole square by 2 sigma square. Now xi is basically individual value, because we were just looking at single value there. Here it's a different story, and this is where x bar. So x bar is what is basically the mean of the total x, and that is basically mean is the prediction of your x, right? So if we take the mean of the overall value, we are saying on an average all the values are close to this mean, right? Likewise, we in the linear regression also we are doing the same thing. Instead of predicting one x, we are predicting one response variable based on different independent variables, and this is the formula which predicts y, right? So theta is basically coefficient transpose of theta into xi. So and whole square by 2 sigma square. Sigma square is your variance, or standard sigma is standard deviation. So now this is for each example, right? So we have to find out the likelihood for each example. But if we have m examples, so we have to find the maximum likelihood of m examples. And this is the probability that we are trying to. So to get the maximum likelihood, we need to multiply the probability of all the values, right? All the examples. And that's why we are using this symbol. This symbol means multiplication of this value for each example. That is what it means. So we have to maximize this likelihood to get the right curve, to get all the values within this range. That is what it is doing here. So instead of maximizing this, we can take the log likelihood of the same function. So we are taking the log of this, so that it simplifies our work. Why? Because when we do the log of products, we can just keep adding log. Let's say we are taking the log of x into y into z. So what it means is log x plus log y plus log z. So since we have to calculate this whole equation, which is nothing but the product of each value. So what we do is we take the log of this, and that transform this multiplication into addition. It becomes additive instead of multiplicative. So then once we take the log of this value, what we get is this. If you calculate the log of this, since this is a constant multiplied by this, so this can come out of this sigma sign. That means this has been repeated m times, right? So this is what it is, m log of this. Then this is in the minus, so when log of exponential, of course the exponential and log get cancelled out. So what you get here is 1 by sigma square into 1 by 2, and this is what you get. When you do the calculation, you know this is what, because there is a square here, so all those things. So this is the after log you get this. Now maximizing this, that means left side of the minus sign is positive value anyways. So to maximize this whole value, we have to minimize the negative part of it, right? So if we minimize the negative part, the whole value gets maximized. So minimizing negative means what? This is constant, this is constant. So all we need to do is we need to maximize this sum of this. If sorry, minimize this. Because if we minimize this, the negative term of this whole equation becomes minimum and therefore it becomes maximum. So we are maximizing this, minimizing this. So this is what we saw, least squares error. So this is the whole idea here. Now assumption in linear regression. What are the assumptions in linear regression? So linearity of relationship between dependent and independent variables. So we look at all of the assumptions. So one of the assumptions is the contribution of each independent variables are additive. That's why we use the equation like, y is equal to theta naught plus theta 1 x1 plus theta 2 x2. So we are basically adding. So the contribution of each independent variable in this linear equation is additive. So we add them all by after multiplying with their respective coefficients. Now predicted value is a linear function of each variable independently. That means keeping others fixed. So what it means is that the relationship of response variable y is linear with each of the independent variables. So let's say there are three independent variables x1, x2, x3. So the linear equation will be y is equal to theta naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 and so on and so forth. So what this is saying is that the relationship of response variable, that is y, can be said as y is equal to theta naught plus theta 1 x1 while keeping x2 and x3 fixed. Similarly, its relationship with x2 would be uh, linear with x2. So it would be y is equal to theta naught plus theta 1 x2 while keeping x1 and x3 fixed. So that this is what this line is saying. So slope of corresponding uh, to each variable is independent of other variables. That means slope corresponding to each variable. That means the theta 1, theta 2, theta 3, that means theta 1 is only dependent on x1 and not dependent on x2 and x3. Similarly, theta 2 is dependent on x2 and not on x1 and x3. Similarly, likewise, theta 3 is dependent on x3 but not on x1 or x2. That's what this assumption is saying. So errors follow normal distribution, as we discussed already earlier with the bell curve and all that. When we say normal distribution, there are two conditions in normal distribution: that the sample, all the samples have to be independent and they have to be identically distributed. That is, they all have to come from the same distribution. That's why all the sample have to be identical in the distribution, and yet they have to be independent of each other. That's what it means. So homoscedasticity of errors. That means when we plot errors, against predicted values or against each independent variable, so we can have all the errors uh, in the y section and all the predicted value in the x section, x axis, and all the errors on the y axis. So what it means is, when we plot the scatter plot, there should not be any pattern in the plot. That means the data should be all plotted randomly here and there. They should not follow any particular pattern, because that is what homoscedasticity means. It means the variance should be constant. If the variance is constant, and when we plot these errors on y-axis and independent variable on the x-axis, or dependent variable, then predicted value or independent variable on the x-axis, the scattered data should follow random pattern. It should not follow any particular pattern. It should be random. Another assumption is that the dependent variable also should follow normal distribution, but this is very difficult to find in real data. So this can be seen later. Now testing for linearity. So plots, there are different plots which we can check to see whether our linearity assumptions are being followed, basically to explain the variability in the data. We'll see. This is what I was saying in the previous video. Here residuals means the errors, and this is the fitted values, right? So as you can see, all the data point, all the errors, these are all errors. They are all scattered. They are not showing any fixed pattern here. When they don't show any fixed pattern, that means our model is performing well, and all the variability in the response variable has been well explained by the independent variables, right? Because y is equal to theta 1, theta naught plus theta 1, x1, theta 2, x2, and so on. So all the variables, independent variables x1, x2, x3 are able to explain all in the entire variability in y. That's why you get this kind of error pattern. Otherwise, there'll be a pattern in that. This is all random. It's not fixed. So this is what this explains the variability in the data. Now here is the predicted value and here is the actual value. See, the predicted and observed value are following, like, it's very perfect example. You won't get to see this kind of perfect example, but it will be like this only. They'll just follow like a linearity. So they are like almost same, right? So violation of homoscedasticity. So when there is a pattern, the errors in the error scatter plot, it's either because, see, this is the pattern. You see here there is no homoscedasticity. It is called heteroscedasticity. That means you can clearly see that it's not random plotting. There is a pattern in the error. So this is standardized residual, and this is your x-axis, your predicted value, and you see there is a pattern here. It's like dumbbell, it's like a dumbbell. So there is no randomness in here, and therefore it does not follow the homoscedasticities. There is a violation here. So what could be the reasons? So linearity assumption is violated. Perhaps the linearity assumption we saw earlier, the normal distribution and all those things, or a relation between independent variable, dependent variable, all those things we saw. So that is violated perhaps. So we need to transform variables, maybe more variable. We need to transform the existing variables to get to that assumption and all that. And then maybe there is a presence of outlier in the response variable, perhaps, and that's why it is showing some pattern. Or the dependent variable is highly skewed, either it could be right skewed or it could be left skewed, so we need to check that out. So whenever there is a problem in the dependent variable, what we do is we can transform the dependent variable as well. If the variance in this plot is constant, that means there is no pattern here, it's all random, then there's no need to change y because it's perfect. But if there is a pattern like this in this example, let's say the constant our variance is directly proportional to the expected y, that means predicted y, then we need to change uh, y, the response variable. We need to take the square root of response variable. If it is directly proportional to the square of predicted value, then we take the natural log of y. If it is cube, then 1 by square root. If it is x to the power 4, then 1 by y. These are the way we transform. When you do model building, you will automatically learn these tricks, and you'll get to the main idea is to practice more model building, get more data, and do all these kind of experiments. Then you understand these things more and you get used to these things more. So again, here we look at, so what is R square? As we saw, R square is basically goodness of fit. Basically, it shows that how well our model is performing, how well it has fit the data. So we'll see how to calculate R. So first what we do is we build a baseline model. It is nothing but the mean of the response variable. So this is the baseline model here. You see, this is the baseline model. That means for every record, our model will predict only the mean of y. There is no change in this, right? This is the baseline. So for every record, the predicted value is mean. That's what we just saw. So sum of a square errors, we saw SSC, right? Which was for the least squares. So here sum of square errors in the baseline model would be y minus the sum of y minus y bar whole square, right? Because our model is predicting only one value, which is mean. So the error would be, we subtract this mean from each value of y and take the square and sum them up. So we get some square errors for the baseline model, and it is known as sum square of total. This is how SST. Then we build our model with all the variables, and then we calculate SSE as we saw previously, sum square error for the model actually which is this line you see here. This is our model with independent variables. So we calculate SSE, and then this is how we calculate R square value, that is 1 minus SSE by SST, sum of square error of the model, sum square of the baseline model, which is known as sum square total, and then you get R square value, and R square value always varies from 0 to 1. So if it is closer to 1, that means model is doing well. If it is closer to 0, that means model isn't doing well. And it is basically, in definition wise, it is a correlation between square of observed and predicted values. That's what it means. So what happens with R square is that if you keep adding more variables to your model, the R square will always increase. It will keep increasing as you keep adding more and more variables. And therefore, we come up with adjusted R square. We'll see what adjusted R square. So again, R square gives a quick assessment of the model, and it is only a descriptive measure. So if we add more explanatory variables, that is independent variables, R square keeps increasing. That's what we just said. So to penalize the addition of more predicted variables, what we do is we use adjusted R square. How to calculate adjusted R square? This is the formula. R square, adjusted R square is equal to 1 minus n minus 1. N is the number of example, and divided by n minus p minus 1. Again, p is the total number of predictors or independent variables, and whole thing multiplied by 1 minus R square. So we calculate R square and then subtract that from 1 and multiply. Another definition of the same adjusted R square is 1 minus residual ms by total ms. So this is called mean square, residual mean square by total mean square. We'll see what that is. So n is the number of examples as we saw. P is the number of predictors, independent variables. So residual ms is basically nothing but sum square error of the model divided by n, the total number of examples, minus total number of predictors minus 1. This gives us residual ms here. And what is total ms? Total ms is sum square total, that is from the base model. We calculated SST divided by n minus 1, the total number of examples minus 1. So if you do this division 1 minus, you get this result, basically the same thing. Now there is another way. So that what we saw, R square, adjusted R square, basically they give us a kind of overall view how the model is performing. There is another way of looking at the same same result, whether our model is performing well or not, and that is called root mean square. What is RMSE? Basically root mean square error, that's what it should be. Root mean square is another way to evaluate the performance of a model. That's what we are doing, right? By using R square, adjusted R square, we are evaluating our model. So root mean square error is nothing, but what we do is, as we saw some SSE, right? Some square error, which is nothing but this term. This term is some square error, right? Error squared and then added. Now we are taking the mean, right? Root mean square error basically. So mean square error is, so we take the sum of square error divided by the total number of example, then it becomes mean of some square error, and we take the square root of that, so that becomes root mean square error, nothing else. N is the number of examples, right? So we divide the data into train. So how do we use this technique? So it's very simple. What we do is we divide the data into train and test. We will see, we'll do another video on how to divide data into train and test data. So training data or train data is basically used to build a model, and test data is used to test whether model is performing well on unknown data or not. So we divide the data into train and test data, and then we calculate RMSE for each and see both are nearly same. If they are nearly same, then model is performing well. So we'll look at one code example here, set.seed, to get the reproducibility. So I'll explain the code one by one. So n is basically we get the number of row in the data. So n row, we use n row function. Now we want the number of examples in the training data. So n1 will represent the number of examples in training data. So we use a floor function, multiply this n with 0.07. So we are getting 70% of the data in training data, right? Floor will give us the lower value, right? If it is in fraction. N2 will simply be n minus n1. So n is the total number of example, n1 is the number of example in the train data, n minus n1. So train will become sample. Now we are using sample to randomize our selection, right? We want to randomly pick up examples from the data. It's not that we want from first to 10 or first to 20. If we are taking, let's say, if data set has got 10 examples, we want 7 in training data and 3 in test data. We don't want 7 from first to 7. We want 7 from anywhere from 1 to 10. So that's why we're using sample. So this will give us the index for train data in a random way. 1 to n is the total number, and n1 we want n1 number of examples from n data, but randomly. So what we are doing is we are creating a random index for training data, and then we build the model LM. So again, the response is on the left side of the tilde and date. So here is another way of building a model. Let's say there are multiple variables in data and we want to use all the variables. So instead of writing down all the variables like x1 plus x2 plus x3 this side, right side, we just put a dot, so it will automatically pick up all the independent variables from the data. And data here, supplying data into train is the index, right, for training data. That's what we discussed. So, and we use the predictive model, predict function to predict the values, right, for M1. And new data is again train. Minus train would mean all the test data, right? So train is the index for the training data. Minus train will become the indices for the test data, right? So that's why putting minus. So we are predicting the values of test data here using this predict model, a predict function. So observed data will be like, the data here, and then response into minus train. So we are collecting the test examples in this. So response is basically response variable. So we are just picking up those values which are there in the test data. And the difference will be the error, right? So this is the observed, the actual value minus predicted value will give us the error. So test.rmsc is square root, as we saw, of sum of the same example of. So this is for double star is for the square, actually for the power. So, or you can also use that upper sign, so difference. So we are taking the square of this, dividing it by n2. Why n2? Because the number of test data, right? And then square root. So this gives us the test RMSE. And for train RMSE, we do the same thing. In fact, the model itself will give us the residual value. We square it, sum it, divide it by the n1, and then square root. So then we match these two values. If they are quite similar, nearly close, then that means our model is valid even based on RMSE. So we can display the values of, Now, while building models in linear regression, one thing we need to understand is that if we have a very large number of independent variables, if you go to the real-time data, there could be independent variables even in hundreds, even in thousands. Especially in biological sequencing data, you will come across many independent variables. But let's not get into that. But what we are trying to understand here is regularization. What it does is it helps us cut down on number of independent variables. We can keep on adding independent variables, but some of the independent variables do not add significant value to our model. Basically, they don't contribute much. So that's why we use regularization in order to remove, eliminate, or eliminate the effect of those variables, or completely eliminate them, because those variables are hardly playing any role. Therefore, there's no point adding those variables to our model and making our model more complicated. Because as we saw, the rule is that we should build a very simple model and it should give highest accuracy, right? Building complex model, adding more independent variables is not a sign of a good model building. That's what we have to remember. So we add a regulation term lambda to linear regression to control overfitting the model. So if you add more and more variable, what it does is also overfits the model. We'll see there's something called variance bias, balancing. So we look at that later. There is another, we'll make another video where we'll see how to balance between variance and bias and what are they basically. Overfitting is basically that model is touching each point instead of like a straight line we saw an example. Overfitted model will touch each point and make line like this, you know. So what it does, it penalizes the overall cost. That means sum of total sum square error with increasing number of variables. So we'll see how it does. So if you add this regulation term, what will happen is if you keep adding variables, the overall cost or the error will also keep increasing along with that. So then in that case, model is not a good fit. So we never regularize the intercept. So bias term, remember theta 0 in the beginning, that is never regularized. We always regularize the coefficients which are related to independent variables. So there are different regulation methods. One is lasso regression. So it's also called L1. What it does is it takes the absolute value of each coefficient and adds them up and then multiply by this lambda regulation term and divide by the total number of records. We'll see the example later. Ridge regression, it is called L2 regularization. Basically what it does, instead of taking the absolute value of coefficient, it squares the, because some coefficient may have negative value, some may have positive. So they will all cancel out. That's why we either take absolute or we square them. And then we add them here, multiply by lambda, divide by the number of records. So this is L2. We'll see. So now there is another method. Basically, when we are trying to build the model, the main challenge is to find out the optimum number of independent variables and the relevant variables. Irrelevant variables or insignificant variables do not make any sense. So there are different techniques. One technique is subset. So we look at how it works. So always try to build a model which is simple to explain with minimum variables and highest accuracy. That's very important. So now there are mainly three types of selecting subset of variables for the model. We look at one by one. For selection. So what we do in this is we start with a zero variable. So y is equal to theta naught. In the next step, we add one variable. So y is equal to theta naught plus x1, theta 1, x1. In the next step, we add one more. So y is equal to theta naught plus x1, theta 1, theta 1 x1 plus theta 2 x2, and we go on like this. Step by step we keep adding. That's why it's called forward selection. Finally we reach a point where there is no improvement in r square value or p or f stat, or there are many other ways, or even RMSE we can check that out as well, root square mean error, also we can do that. So looking at those parameters, we see that there is no more improvement by adding more variables, so we stop that. That's how it works. In backward elimination, it works just the other way around, So what we do is we start with all the variables. So the first model will be y is equal to theta 1, theta naught plus theta 1 x1, theta 2 x2, goes on to theta m x m, where m is the total number of variables, right? And then we keep dropping the one by one. So the next model will drop one variable, the variable which is least useful, depending on p value and other r square value and so many other factors. So we keep dropping, and then finally we reach a point where there is no more, when we have included all the useful variables and let go of all the least useful variables. Stepwise, this is another way. In this case, what we do, it's a mix of forward selection and backward elimination. So we keep adding new variables and also keep dropping the variables which are not useful. And there is a function step in R, so this simplifies our job. If you use step function in R, that automatically takes care of, and then you can, in the argument, you can give the option whether you want forward selection, backward, or stepwise. It does the job for us actually. That's a very good function in R. Another lengthy process is called, other than these subset, forward selection, backward elimination, stepwise. The lengthy process would be exhaustive search, where you look at all the possible subset of variables, which is very cumbersome task and computationally very intensive. So it's not a very good idea. Now we'll look at the algorithm behind linear regression. So the main objective of linear regression is to minimize the cost function, right? That's what we saw in square root some square error, right? That's what we saw. Now, how the cos function is defined, this is j theta. Now, it's a little different from how we've defined earlier, but I'll just explain to you. This you saw in the likelihood also, the same formula. Yi minus theta transpose xi square. So this is what we are trying to minimize, right? And we divide it by 2m because we saw in the likelihood, because when we take the log, this 2 comes here. M is because we are taking the mean of this, mean of the overall error, and we are trying to minimize it. This is for the simple linear regression, right? This is how, this is basically the cost function, that the one which we are trying to minimize. If you are looking at the multivariate, that means more than one independent variable. So this is how you write the cost function. Instead of in model building and in machine learning, we try to minimize our calculation and minimize the for loops actually. So you can also write the same equation in this form, and then you add one more for loop for example, one for loop for example, and another for loop for each variable. Instead of doing that, what you can do is you can keep the for loop for each example. You can get rid of for loop completely if you use the vectorized version. Vectorized version means you take the matrix form of each parameter here. So why you take the matrix? That means it could be a column vector, all the response variable in just one go. X is the matrix of number of examples, and columns will represent number of variables. So each column is one variable. Theta naught, again, it could be a column vector because it has all the different values for different independent variable. Both are same. Instead of taking square, we take transpose and multiply. You get the same thing. So it simplifies the calculation of doing two for loops. We are doing it in just one line of code. It can solve the problem. And regularization, this is the regularization term which we saw. So this is the lambda regulation term divided by 2m, and instead of theta square, we are doing theta transpose theta because we are taking the matrix form, right? Vectorized version. So this is regularization term here. Now gradient descent. What is gradient descent? See, I'll explain the gradient descent in a very brief way. So let's say this is our function, and we want to reach the global minima, right? We want to minimize the cost, right? So we want to reach the global minimum. This is the global minima here. Okay, this is the minima we want to reach. So if you want to minimize a function, if you take the derivative in mathematics calculus, derivative is nothing but the slope of that function, right? So if you take the derivative of this function, that gives a slope. So where will this value become 0? Where will the derivative of this, where the derivative of this is 0, right? That's the place where this becomes minimum. To minimize this, we need to reach this is the curve, right? If the minimum value is here, that means the minimum value of this is here, not here, not here, but here. This is, and if we take the derivative of this function at this point, it will become a flat line here. That means the slope is 0. So the derivative of this should become 0, and that is what is called gradient descent. I'll explain a little more. So if you take the derivative of this cos function with respect to theta, this is what you get. 1 by m summation of y, this is for this one, simple linear regression. And the x comes out this, right? With the respect of theta, if you do, this is the formula you get. You can do the mathematical calculation on your paper and you will get this formula only. And if you do take the partial derivative of this cos function with respect to theta, this is what you get, right? So it's the same thing basically, because we are doing vectorized version, so there's no need for summation sign here. So 1 by m, and 2 gets cancelled out, 2 gets cancelled out because of the square, and then that's it. Y minus theta transpose x, total transpose x, and then plus regularized version. This also gets theta, so theta square basically it is. So 2 gets cancelled out and lambda by m into theta. One thing you need to remember in vectorized calculation is that take care of the dimension. Okay, so this is single column vector matrix. So after multiplication, this also should become a single column matrix. Then only you can do the subtraction. So take care. This is like, let's say this has 3 variables. So it will be either you transpose this or you transpose this. Make sure that this dimension is taken care of because it's a matrix multiplication. And then again, this is also matrix multiplication. So whether X will come here or it will come here, whether transpose will be on this or on this, you have to take care of that. This is how it's written, but depending on how you have arranged your X, so in some people, what they do, instead of using column as variables, they use row as variable and column as example. So depending on how you represent X and Y and theta, take care of the dimension here when you're writing this formula particularly. So, so basically this is what it is, the cost function. The idea is to minimize the cost function. To minimize the cost function, we take the gradient descent of this, gradient of this, which is partial derivative of this with respect to theta, and which is nothing but the slope of this function. And wherever the slope is 0, this gets minimized. That's what it is. Simple as that. So how do you update? Once you calculated gradient, what do you do? How do you update theta? Because the idea is to get to the optimum value of theta, right? That's what we want to do. So how do you update? So this is the updated, this is a formula for updating your theta. Theta is updated, theta is equal to theta, original theta, minus alpha into grad. What grad you calculated here? What is alpha? Alpha is a learning rate actually. Learning rate can simply be explained. Let me do some graphics here for you. So let's say there is a ball here. Sorry, not able to. Okay, here. 1 second. Not this, but this. I'm just trying to draw something for you. Let me draw something for you. So what I'm trying to show you is, sorry, my drawing is not so great, but just to explain. So basically what we do is, when we take the partial derivative and when we multiply with this learning rate and subtract, let's say the original value of theta is somewhere here, right? We are minimizing the cost, right? So because of the theta value, the cost is here. But when we multiply with this alpha, this learning rate grad, and then subtract from theta, now because of a new value of theta, now it has come down here. It has come down. So keep at every iteration, it keeps coming down, and then it reaches here. If it is this side, then again it keeps coming down, and it comes and reaches here, the global minima, right? However, this movement also depends on the shape and size of this ball, right? Let's say this is in the form of ball. If it is too big, then it may come here and straight away go here instead of coming here. If it is too small, then it may take very long time to reach here. So this is what learning rate does actually. This is the job of the learning rate, to ensure the shape and at what rate it is moving towards global minima, and how fast it comes here actually. That is the whole idea. Now I'll give you a sample code for algorithm that we discuss here. So basically you see, uh, it's very simple. Basically you can just have a look. It's nothing but the same formula which we discussed. So I have given for the regularized and multivariate no linear regression. So this is the cost function 1 by 2 m into transpose of x into theta minus y, and the whole thing multiplies by x into theta minus y plus lambda divided by 2m into temp y, because we don't regularize the theta 0, right? So that's why the first uh, coefficient theta 0 has been set to 0 when we are doing this. So that's why here we are using theta, but for regularized term we are not you are using temp. That's a temporary, that means another variable for theta, but we have set the first theta not to 0 actually, because we don't want to regularize that. And then this is the code actually. I've given a very sample code, and based on this code you can spend some time looking at this code and build your own model. This is basically a function. It returns j theta, sorry, the cost function basically. And then again we do the same thing for gradient descent. So we calculate the grade 1 by m into transpose x. Now again there, if you remember, the x was this side, but because of the dimensionality, I've used this transpose x into theta minus y. There's no transpose of theta here. Here also, if you see, there's no transpose of theta. So that because of dimensionality, and it is a vectorized form, that's why. Plus lambda divided by m into temp. Again, temp because we are not regularizing the uh, intercept or the bias term. And training the model. So here is the, see, for a very large number of data, huge data and large number of variables, there is a function called optim in R, and it takes certain arguments like par. So here initial theta, you can initialize theta by all putting all as 0 or some random. There are methods to initialize theta, to give initial value. Then here you give the cost function. Fn is the cost function, linear regression cost function. Gradient, this is gradient. So linear regression gradient function, this function, here this function. But you have to write a function. This is just a sample code for both. And then method BFGS. You can do some research on these methods. X is equal to X values, Y is equal to Y values, lambda regularized term. So you can define your lambda value yourself. Give some lambda. Controlling list maximum iteration is 200 times, and it will automatically build the model, train the model for you, and this will give you the value and theta. So basically we are just trying to get theta, right? Once we have theta, then we can build the model. So I hope this video has been helpful to you. I know it's a very long video, but I had to do it because there are still some more topics related to linear regression, like how to divide test data and train data, and there are like p-values, and there are some other like bias and variance, how to balance them and those things. So I have to make a separate video, but I wanted to cover all these topics. That's why this video has gone a little longer. Bear with me, and thank you so much for your precious time, and I hope you like this. It has added some value to it. I'm not saying that I've given you all the details. I've just given you a little foundation to start with, and to start your data science journey with linear regression and with the previous videos. So this is all overall, but I'm sure if you go through this video, pay attention carefully, you will get the gist of the whole thing, and then you are on your own. Then you can do a lot of online research and get to know more about different techniques and different nitty-gritties and details. But going through this video will give you some idea, not some idea, but it will build a basic for you, and based on that you can build your own castle. So that is how it is. Thank you so much. If you like the video, like, share and subscribe, and also comment. Thank you.